For the next part, we return to the associated Legendre equation for arbitrary integers m and l with m between 0 and l, and we like to show that the solution is the associated Legendre function plm, which is given in terms of this formula involving a function of x times the mth derivative of the ordinary Legendre function of the first kind. The whole point of the problem, then, is to show that the m not equal to 0 case can be reduced to the m is equal to 0 case. Again, remember that this is a second-order differential equation, so you do expect to have a general solution composed of the associated Legendre functions of the first and second kind, but the associated function of the second kind, QLM, is unbounded at x equal to plus or minus 1, so at least within the context of bounded solutions, we only care about PLM. Next, we write y is equal to x squared minus 1 to the m over 2 times v of x, and substitute this ansatz into the differential equation. What we like then is to show that v of x is the mth derivative of the ordinary Legendre function. So you have to go ahead and compute the first and second derivatives of y and substitute it into the differential equation and simplify. Rather than doing this by hand, we can use Mathematica to do the algebra. In Mathematica, I first clear the worksheet and then I define the function y of x as x squared minus 1 to the m over 2 times v of x. For example, I can then easily write down the first and second derivatives. I can now define the left-hand side of the associated Legendre differential equation and simplify the result. Returning now to paper, we can see that when the ansatz is substituted into the equation, we can pull out a factor of x squared minus 1 to the m over 2 minus 2, and our mission then is to find the function v such that the curly brace portion is 0. This requires you to look ahead. We know that the solution is going to be proportional to the mth derivative of PL, and in fact, all the equations we're dealing with are homogeneous, so we can just ignore any constant prefactors in front, such as the minus 1 to the m factor. If you look at the equation that defines PL, that is, the Legendre equation with m is equal to 0, then it looks pretty close to what we have in the brackets. So if we take m derivatives of this equation, the question is, do we recover the expression within the curly braces? So again, we apply Leibniz's rule and write out the summation term by term until the later terms are 0 due to the differentiation of the 1 minus x squared factor. Simplifying, we get a left-hand side that's a second-order differential equation in terms of the mth derivative of PL. Now go back and look at the expression within the curly braces. This is exactly it. Therefore, if we take v to be the mth derivative of PL of x, then the associated Legendre equation is satisfied. Again, because the differential equation is homogeneous, we can multiply it by the constant factor minus 1 to the m, and we've derived the solution to the associated Legendre equation.